Let's adjust our intervals based on this. Okay, so this, should I just erase them? What do you think? Erase them or maybe make a note that we have to adjust for sample size and do better ones over here? Yeah, let's do that. Let's do that. That way we don't throw away all our work. It's good work. I love what you guys did. Going 2 standard deviations away is fantastic. The only problem is if you go 2 standard deviations away, you're only talking about your sample, not the entire population. In order to talk about the population, you have to convert your standard deviations to standard errors. To standard errors. You have to get the standard error calculation. And this is another one of those unfortunate things in statistics that has too similar a name to its friend, the standard deviation. We mentioned this, again, we're looking at the last week of 243 here again. I apologize for bringing that back up again. But the idea is when you take the standard error in your sample, literally, the standard error of a population is its population standard deviation divided by the square root of the sample size. But we don't ever get little sigma, so we apply S divided by root n instead. That's the best we can do. We can't get little sigma unless I go out and buy every single Del Taco half-pound bean and cheese burrito. Exactly. And imagine the high blood pressure, cholesterol, everything else you're going to get from that. I guess you don't eat them, you buy them. That's wasteful. So we're going to take this. Let's adjust that based on our sample of size 30. So for us, that's 0.025 pounds divided by the square root of 30. Let's calculate what that is real quick. Let's calculate what that is real quick. S divided by root 30. I get 0.005. Can we live with that? I'm going to go 3 decimal places of accuracy. Root 30, technically I've got infinite accuracy because I have a computer. So we'll call that 0.005. Well, that's a lot narrower than that's 1/5 of 0.025, yes? Yes?
How did you do the SC in there like that?
I'm magic. I'm sorry, I'm kidding. It's a trick I taught you on a quiz in 243. If you press the vars menu, which is directly to the right and diagonally down from stat, it's where all the variables on your TI live. And if you press that and then go to statistics, you'll see listings of all the stat variables that you have. Not that you need to use this a lot in this class. I'm just using it now as a quick example. And then that way I can get all that unrounded accuracy, precision that I didn't want to lose any of that. But the important thing, don't worry about that. Concern yourself with the value that I just got. 0.005 pounds, yes? That's much narrower than the sample standard deviation. Because the central limit theorem says it has to be, yes? The central limit theorem says it needs to be narrower than the sample standard deviation. Because with every increase in sample size, we get more and more precise. So now you can see if we had a sample of size 300, that would shrink down even more. Because we'd be dividing it by an exponential, a multiple of root 10 number. About 3 times narrower. Can we adjust our intervals now?
Yes.
I think. Because this wasn't taking care of the inferential bit. This was only taking care of our sample. Let's adjust it for inference. We can see that okay? No, we can't. Let's turn this off. Move this, slide this over a smidge. Zoom back a little bit. Good. So, let's do 68%, or you want to just do 95% confidence? Why don't we just go 95%? I mean, it seems to make the most sense. Nobody's going to go 68%. That doesn't make any sense, right? Let's go 95, right to 95. So we're going to take this guy right here, x bar plus or minus 2, but it won't be x bar plus or minus 2s anymore. It's going to be x bar plus or minus 2 of the standard errors, which is the whole point. AKA, if you multiply a standard error by a multiplier, you don't call it a standard error, the press doesn't call it a standard error, scientists don't call it a standard error, they call it a what error? Margin of error. That's what you now have for 95% confidence, yes. So rather than just talking about your sample data, you are now making an inference. You are now making an inference about the entire population of Del Taco half-pound bean and cheese burritos. You're not as excited as I am about this, that's okay. Let's do it. So we're going to have x bar, which is still 0.526. But now we gotta dump 0.005 off of it. So if I take 0.005 off of 0.526, I get 0.521, yes? Pounds. Comma, and if I add 0.005 to 526, 531? Did I do that right? Did I do the math right on that?
Yeah.
I hope I did.
Standard, that's a single. You didn't double it.
Yeah.
This is
Oh!
higher.
Crap!
I'm like,
Sorry guys, I'm adding 0.005 times. Sorry, I did that 68% confidence. I didn't do the 2. So I have to add 0.01 to each. Thank you
Yeah.
guys for looking. I see confusing looks, that means I screwed something up. Yes, so if I add 0.01 and subtract 0.01, 516. Make sure I did this right. And if I added 0.536. Is that better? Is that fair? Good, correct math that time. Whew. Thank you. Whew. Forgot to double the damn standard error. Whew. Big. Katie's like, okay. I was having a good nap till he yelled. How do we feel about Del Taco calling their half-pound bean and cheese burritos half-pound bean and cheese burritos?
good.
Why do we feel good about it?
Certified half-pound.
Aha! 95% confident that they're more than half a pound. You see what that? So if you imagine a number line again, if you imagine a number line with half a pound on it, this is pounds.
The margin of error is above that.
The lowest point of that interval, the lowest point of that margin of error, Nick, is above half a pound, which means we're basically at 0.52 up to 0.54. So here's Del Taco half-pound bean and cheese burritos. I'll just make this go out. Average weight. At the absolute lowest, it's at 0.516. At the highest, it's at 0.536. But the idea is, even at its low end, it's still above a half. Which means I think they've covered themselves pretty well. Put 2 more words on there.
On
They've,
average.
yes, they've covered themselves on average, yes? They've covered themselves, take a look, and I think we can actually prove this to some degree. I'm gonna pull this back and show you what I'm talking about.